Hello and welcome to Thermal Live. My name is Graham Kilshaw. I'm the Chief Media Officer of Electronics Cooling Magazine, and we are the creators of Thermal Live. If this is your first time at Thermal Live, this is a 3-day event hosted online by Electronics Cooling, and it features practical education presentations around all aspects of thermal management, including roundtables, webinars, videos, discussion groups, and our very exciting Thermal Product of the Year competition. If you have not voted yet for your favorite thermal management product, it closes today at 5 p.m. Eastern Time. You have a couple of hours left, so get moving. There's no cost to attend any of this week's events. They're all free. So join us for more presentations later today and tomorrow. Today's webinar is Liquid Cooling, Practical Guidelines to Design and Manufacture, presented by Wakefield-Vette and Richardson RFPD. It's presented by Mark Pelillo, the Director of Engineering at Wakefield-Vette. Mark's been in the electronics cooling design industry for over 25 years and has been a pivotal part in introducing new technologies to this marketplace. Wakefield-Vette and Richardson RFPD together provide thermal solutions across multiple industries for all size businesses. There will be a recording of this webinar and downloadable PDFs of the presentation available on our Thermal Live website next week. So look for those shortly. And if you've already registered, which you must have since you're listening, we'll automatically send you an email with a link to the recording and a link to download the slides just as soon as they're available next week. So no need to contact us. It'll automatically come to you as soon as they're available. This webinar is interactive. You'll be able to ask questions throughout using the instant message tool to your right. So we encourage you to do so. On the right-hand side, you'll see a box labeled question. Simply enter your question and hit send. We'll try to answer most or all of the questions at the end of the presentation. If at any time you wish to minimize or maximize your screen, just use the red arrow button. And if you have any issues during the presentation, please also use the question field. Mark's presentation lasts about 35 minutes, and then we'll have about 10 minutes available for questions and answers. And now, Mark Pelillo will begin the presentation. Over to you, Mark.
Thanks, Graham. So what I want to talk today about is the design and manufacturing of cold plates. So Wakefield-Vette has been a supplier of thermal management solutions since 1952. We supply a number of industries from Fortune 500 all the way down to very small businesses. And we deal with power conversion, IT, aerospace and defense, medical, consumer, LEDs, basically anything that requires a thermal solution. And part of the partnership that we have is with Richardson RFPD, which is a division of Aero, and they're a distributor who specializes with supplying engineers with design engineers and technical background so that you can go out and solve your products. Richardson also happens to be one of our largest distributor partners, and they'll carry most of these products that we're going to go through today. So what is liquid cooling? It's the natural evolution beyond air cooling. You'd go to liquid if for some reason your thermal requirements or your footprint requirements cannot be met with air cooling. You can always say I could go get a jet engine to produce enough airflow, but that may not be economical. So that would force you to go into a liquid cooling application. When you look at liquid cooling, you want to look at what are your thermal resistance requirements. For liquid cooling, we define that as your average plate temperature minus your incoming fluid temperature divided by the total power going into the plate. And you also want to take a look at what is your pressure drop, usually measured in PSI, but again, you can convert that into metric units as well. Liquid cooling is most often done via a tube, whether that be made out of copper, aluminum, or stainless steel, embedded into a separate base material. Now you can also do this by machining a channel or forming a channel in the base material directly, in which case your choice of materials may be dictated by your fluid. So when you look at what are your different fluids, water or a water glycol mix are the most common. But we've also looked at fuels, whether that's a jet fuel, gasoline, a propane, or another liquid form of a fuel, oils, liquid refrigerants, or even a two-phase refrigerant. Typically, it's what is available at the site you're going to be working on. When you think about air cooling, it's important to maintain good quality air. You don't want a lot of dust and debris blowing through your heatsink that just reduces your performance. You have the same criteria for liquid cooling. So I have up here a set of generally accepted good criteria for water. And in a lot of cases, this is achieved by adding antibacterial, antifungal materials into the water, either by swapping out water or by adding these on a weekly or monthly basis. A lot of it will depend on how large your system is, what other components are in your system. So the first product I want to talk about is the rolled tube or R180 series. We'll start with an aluminum extrusion that has a series of channels in it. The ones that are shown have 2 channels, but we have others with 4 and 6 channels. You'll take a thermal epoxy and basically paint the channel, put your tube down in it, and then roll the aluminum extrusion over the tube to capture it. Now you have a solid conduction path from your source through the aluminum into your fluid channel. Typically, these are done with a 3/8 copper or a stainless steel tube. You try to line these, you try to pick the ones you want based on the size that you have available and making sure that your tubes are actually underneath your devices. The biggest limitation with these is you have to have that profile tooled in order to move your tubes around if you want to do something non-standard. We can do custom shapes if required, but there may be a minimum order associated with the amount of material. The next style is a full buried. In this case, the tube sits completely below the surface of the material, and that channel that the tube is set in is backfilled with the same thermal epoxy. We'll come back, we'll machine both sides of the plate to make sure they're nice and flat, nice and smooth to give you good thermal contact. And you can actually put devices on both sides of the plate. Typically what we find here is people will put their higher power devices on the bottom side, the solid aluminum side, and then put lower power devices on the epoxy side because you will pick up extra thermal resistance going through the epoxy. This is typically done for 1/4 inch through 1/2 inch, although we've done some designs with 5/8 and even 2-inch tubes, depending on what the criteria is and what your flow rate is. Your biggest design limitation here is what is the bending radius. You want to keep in mind that you would really like to keep one standard radius throughout the entire tube, as that makes it easier both to produce the tube as well as the programming of the CNC operation. As we move up the evolution chain to try and get better performance, we go into an exposed tube. Now in this case, the copper tube sits in a shallow channel. It is backfilled with the same thermal epoxy. But when we do our machining operation, we take off a small amount of thickness of the copper tube itself. Typically we do this with a 3/8 or a 5/8 tube. We've dropped out the 1/4 inch and smaller because those are only available with thin wall, and after they've been machined you don't necessarily have enough wall thickness to be able to support the internal pressure that you may be running at. Same limitation as your full buried. You have to worry about your bending radius. How many passes can I physically put underneath my device? Now with both of these designs, you have to look at, this is a serpentine, so you're going to take your heat from your first device to your second and to your third, and your pressure drop is based on your total tube length. I'll show some designs later where I introduce a manifold design which can help you introduce cold fluid to multiple devices or even lower your pressure drop. Half buried is another style where customers are not wanting to do a lot of machining operation, and we try to do this only in copper so that we can solder it or braze the tube to the plate. The thermal epoxy, while has some structural merit, may not survive a side load, and so therefore you could actually separate the tube from the plate if you're not careful. These are typically done with 1/4 inch through 1/2 inch tubes. You have the same limitation of your bend radius, but you do have a little bit of flexibility. You can now, because there are no standards for this, you can move your tubes around to get them directly over your devices. A deep drilled part, we'll start with solid aluminum or solid copper, and we'll drill a hole halfway down the part or all the way down the part based on its length. If we have to, we can drill from both ends and the holes will line up in the middle. To establish your flow path, you'll drill a series of cross channels and then you'll plug off the channels that you don't need. Coming up with a very complex flow pattern can be very difficult with a deep drilled design. But if you're just looking for something simple and you want a quick prototype, this can be an option. Now, from a design limitation, you have to worry about how you're going to establish your flows, but you also want to look at how much pressure drop you're going to end up with, because all of your corners are 90-degree corners. So you're going to have a lot of extra pressure that's built up, and depending on what your flow rate is, you may have an issue with erosion inside the plate itself if your fluid is moving too quickly. The design that's shown on the screen now is a manifolded design. This is a counterflow design, so we have cold fluid going in opposite directions around the plate itself, one going clockwise, one going counterclockwise. By bringing in a fluid and splitting it in half, we essentially have lowered our pressure drop, but maintained the fact that we now have a more uniform temperature on the plate itself. This design is also a sandwich style. You start with a plate on the bottom, tube in the middle, and a secondary plate on the top. You can put devices on both the top and the bottom and provide equal cooling to both sides. This particular plate was designed for about 7,600 watts at 3 gallons per minute. And as a frame of reference, the plate is about 3 feet by 3 feet. As you move away from your traditional tube style designs, you work into a two-paste braze solution. I'll start with your base metal. You machine your flow passages into the metal itself, and then you can braze the two halves together to form your complete channel. Now, the channel doesn't actually have to be in the middle. It can be off-centered to just one side so that your cover is just a nice thin sheet, or it can be in the dead middle. You can vacuum braze or dip braze these depending on your configuration. You can also add machined finned areas within the channel if you need additional cooling in specific areas. In addition to machining the fins, you can also insert folded fin or a separate fin structure that again increases your surface area as the fluid passes over it and allows you to get better performance in a localized area without having those fins everywhere in the plate. Another alternative to a braze design is a welded design. This one here happens to have a perimeter weld as well as some internal spot welds to so that as you pressurize the unit, you don't have to worry about this unit wanting to deform because of its internal pressure. Same thing here, where you can have either machine fins, you can have folded fins, or you can have some secondary fin structure specifically where you need it in order to provide your extra cooling. As we look at the summary chart, we have here kind of a breakdown: cost, performance, and your flexibility. The rolled tube is going to be your least amount of cost. It's also going to give you your least amount of performance. And assuming you're not going to do a custom extrusion, it provides the least amount of design flexibility. Your full buried, your exposed tube, we start to move up in terms of performance and a little bit up in terms of cost. When you get to the two-piece braze design, your cost is the highest due to the brazing operation, but you also have unlimited amount of performance. If you can think of the layout that you want, then you can program it in a CNC, and you can come up with a way of forming that inside the cold plate itself. Some customers don't like braze or don't want to go through the expense of braze, and so they'll do a gasket or an O-ring design. Cost is significantly less. You get about the same performance. You don't get equal spreading from top to bottom from the heat, but you do end up with the same amount of design flexibility. A little bit of extra assembly work because you've got to put all the screws in order to capture that gasket and make sure that you have it sealed. Then you have the sandwich style design. Again, plate on the top, plate on the bottom, usually split in the middle with your tube in the center. Now, with that particular case, you can also use a stainless steel tube because we're not going to actually machine the tube. One of the things we try to avoid is cutting from aluminum into copper is not a problem, but stainless steel being as hard as it is, tooling doesn't particularly like cutting through aluminum and stainless at the same time. And that's all I have today. Are there any questions?
Well, thanks, Mark. Great presentation. Hope everybody found that useful. And as Mark says, now it is time for the questions. If anybody has a burning question, now is the time to enter it, please. There are quite a few questions here, Mark, we're going to go through. And while we're lining those up, if any of our attendees have any additional questions, you can either send them to us after this presentation at info@electronics-cooling.com. And if you'd like more information about the field of liquid cooling, then just look up the liquid cooling section on the Wakefield-Vette site. So Mark, a few questions for you from today's audience. Now, the first one is, are there any applications that liquid cooling technology should never be used for?
If it's not, you have to look at the economics of your liquid cooling. With air cooling, you have to provide a fan. With liquid cooling, you're going to have a pump, and you're going to have a way of rejecting the heat into the ambient temperature someplace outside, so you're going to need an external radiator. So from an economical point of view, you may find that it is more beneficial just to go get that bigger fan, or if your space constraints are really that small, you may need to stay with the liquid cooling. Provided your ambient and operating conditions allow for liquid, if you're going to be running in a -20°C ambient, then you may have to worry about doing a water glycol mix. That may not be able to give you your performance, and so it's a trade-off that you have to look at once you get started.
Okay, thanks, Mark. Good answer. Here's the next one. Can you give us some examples of non-traditional fluids that are used?
So we've done jet fuel, liquid refrigerant, hydraulic oil, Again, these are fluids that were present where the cold plate was going to be placed. So an airborne application, you may not have access to water glycol. You may have to use the hydraulic fluid or even the jet fuel itself that's fueling the engines in order to provide your liquid cooling.
Very interesting. Jet fuel. I never would have bet on that one. Very interesting. Next question. What's the most economical alternative for design, validation, prototype testing?
So one of the surfaces that we offer is a CFD analysis of your design. We will go through and build a mock-up of the plate, analyze different fluid passages, look at the different construction techniques. Is it manifolded? Is it a full buried? And generally, we can get pretty close to the required thermal performance that way, so that you're not spending a lot of time and energy building a prototype, testing it, finding out it doesn't work. We do all the simulation work up front. We get 99% of the way there, go off and build one prototype, you test it. There may be some secondary tweaks after the fact, but at least you haven't gone off and spent a massive amount of money on prototypes which didn't work.
Okay, so I guess the answer there is to have you guys do it. That seems very economical. Let's go to the next question. Actually, this one's from me. I'm curious, Mark, when you're looking at a particular application or a particular situation, what's the number one key factor when you're determining whether you're going to use liquid cooling over natural or forced convection methods?
The first one you want to look at is how much space you have available. If you have a very large amount of space and a small amount of heat density, then you can probably get away with natural convection. As your space constraint starts getting smaller and smaller, then you're going to introduce some form of forced air, whether that's a fan or a blower. And then as your constraint gets even smaller and smaller, that's when you're going to have to be going into the liquid. That's when you're going to be forced to go to something other than just air or natural convection.
Great. Next question, and we do have quite a few still to come. Does utilizing liquid cold plates help to keep a low variation in temperature change?
So if you do a serpentine tube on a plate, your cold fluid comes in, it passes under the first device, and the fluid continually gets heated as it passes under all your devices until it exits the plate. So that's going to give you a large temperature variation from start to finish. If you do something more like the manifolded design that I showed, the sandwich style, where you've got a counterflow design, you can actually reduce the amount of temperature variation from left side to right side, front to back, however it's being laid out, by coming up with alternative flow characteristics on the plate itself.
Okay. Next question. Mark, when engineers are using different materials, does that alter the fluid's flow?
You have to, when you're going to look at your different materials, like if your fluid is a deionized water, that should never be used with a copper tube. You can use a high-grade aluminum, or you can use stainless steel. So that may limit what you're allowed to do from a thermal perspective. So having internal fin structures with a brazed design and having either machined fins or folded fins, that may not work with your fluid type. And that's one of the big things that has to be considered as we go through our design analysis is what's the compatibility of fluid to the cooling technique that we're going to propose.
Okay. Our next question comes from Tejas Shah. He's asking, what's been your experience shipping liquid-cooled systems pre-filled?
We have done it, although I prefer not to. What I would prefer to do is to pressurize the system with, say, a nitrogen environment. That way there, when the customer gets it, there's usually, when you open up that fill valve, you get that first of air, right, that release of air, so that you know the system has shipped and it hasn't had a leak, you know, as a result of the shipping. There's been no damage to it or anything else. Shipping with liquid can be quite challenging. It adds weight, it adds cost, and it adds a lot of complexity that we try to avoid if at all possible.
Okay. This question comes from Santosh Raju. He's asking, are there any types of coatings used for mitigating corrosion?
Internal to the tube, you can look at doing, say, a clear chromate, which will help a little bit. We've also looked at doing running a Teflon fluid through the tube initially, so that you actually coat the interior of the tube with basically a Teflon, in which case now you've limited the fluid's ability to form the corrosion and the bacteria and everything else. For customers that don't want to go through that, that's why we recommend adding the additives to the fluid itself. And in a lot of cases, you can just add a small amount of glycol. 5 to 10% glycol in a water mix is enough to give you your antifungal side and your antibacterial levels that you need without having to add all the extra stuff later on. So a lot of customers will choose just to thin the water with just a small amount of glycol to take care of all of these problems.
Okay, good to know. All right, the next question's in two parts, Mark. It comes from Siang So, and the questions are these. Does thermal resistance increase with larger pressure drop? And the second part of the question is there a simple way to calculate pressure drop?
Does thermal resistance increase with pressure drop? Your thermal resistance is going to be a function of whether you have laminar or turbulent flow in your pipe, which is going to determine your heat transfer coefficient. So long as you can maintain your heat transfer coefficient at that given pressure drop, it shouldn't matter what the pressure drop is. So as I run my calculations, in order to get turbulent flow, which will give you your best heat transfer coefficient, you need, let's say, 2 gallons per minute, and that comes at 5 psi of pressure drop. So long as you can maintain that 2 gallons a minute, whether I change from a full buried to an exposed tube, shouldn't make a difference in the thermal performance itself. Now, as for how to calculate the pressure drop, there are some basic formulations out there that you can use. K's in London is a good example on, you look at how many elbows you have, or how many 90-degree bends you have. A U-turn would count as 2 90-degree bends. You look at what the straight length is, and then you can calculate what the pressure drop is based on the fluid's characteristics. If you get into a more complex design where you have manifolds, internal fin structures, and that becomes a little bit more complicated. That's one I would run through a separate program like a macro flow, or even to do a simple CFD analysis where I'm not necessarily looking for temperature, I'm only looking for the fluid flow through the system to predict the pressure drop.
Okay. Our next attendee is asking if Wakefield does friction stir welding.
It is a technology that we've started to produce some parts with. There's a lot of variables that go into the friction stir welding. So it's something that we continue to work on, and we will have more cold plates that we'll introduce as standards based on that technology later, probably next year.
Okay. Not sure if we can answer this one, but let's give it a shot. It's another two-part question, Mark. What is the difference in reliability? I'm not quite sure what this attendee's asking. Maybe he's asking what are some of the differences in reliabilities? And is there an estimation for pressure loss for the different variations?
So reliability, if you have a tube-based system, all of the cold plates that we produce are pressure tested before they leave the facility. The level of pressure testing depends on the customer's requirements. Most customers will ask for 3 times the operating pressure, just as a rule of thumb. But there are certain constraints where they're looking for 5 and 10 times the operating pressure just for that added extra of safety. So your reliability, if you're using a tube base, is you're going to have very good reliability. Your biggest place that you're going to worry about it is going to be the joints where your connections are made. The tube itself, once it's passed the pressure test, should not ever leak after the fact. Now, when you do a brazed design or a welded design or even friction stir welded, you do have a lot more joints, and that depends on the integrity of the joints as to what your reliability is. So now, in addition to worrying about where your connections are made, you also have to worry about that cross-section where the two plates are joined together. And what's the second half of that one again?
The second half was, is there an estimation for pressure loss for the different variations?
So, assuming the question is related to a rolled tube versus a full buried versus an exposed tube, on the website where we've released these products for different flow rates, we do provide what the pressure drop associated would be. Now, those are going to be for the standards. If they wanted a custom solution, again, it would be part of the CFD analysis, where we would go off and custom do a design and actually predict it for them.
Okay, thanks, Mark. I hope I'm going to pronounce the next attendee's name correctly. Mr. Abdurrahman Idamir is asking the question, is there any other solution for achieving leakage-free cold plates instead of brazing?
A tube-based cold plate can be used. I've never had a tube-based cold plate ever leak on the ones that we've produced or that I've seen in the industry. Again, your biggest point of failure is usually at the connector level, but the tube itself won't fail. There's lots of different connectors out there. There's different pros and cons of each one. But if the part is designed correctly, you should be able to achieve a part that doesn't leak, regardless of its construction method.
Okay, here's an interesting one from Farhad Mohammadi, talking about electric vehicles and hybrid electric vehicles which have liquid cooling. Are there any special concerns there, Mark?
In certain cases, depending on the voltage that the batteries are going to be running at or that the entire system is going to run at, some people get nervous putting a water or even a water glycol mix that close to a high potential. What we've seen some customers looking at doing is using deionized water. Deionized water has you strip the ions out using a special process. It lowers the electrical conductivity of the fluid while for the most part maintaining its thermal properties. The downside to deionized water is it's extremely corrosive. It should really be used with stainless steel tubing throughout the entire system. If you introduce brass or copper, the fluid will actually start to erode the pipe from the inside out, and as it does so, it actually picks up ions from the copper or the aluminum, and then you gain back the electrical conductivity that you work so hard to take out. So that's probably the biggest concern that I see some customers looking at, but most of them are not operating at a high enough potential to worry about the electrical conductivity of the fluid.
All right, good to know. Just so you know, Mark and attendees, we still have a good 6 or 7 questions to go. These are great questions, and our friend Santosh is back again. His question now is, can you please comment on the flow modeling which governs equations for a cold plate?
Okay, so you're going to look at the Navier-Stokes equations that are associated with the fluid flow. You're going to look at what are your Reynolds numbers, what are your Nusselt's numbers. There's all sorts of equations that go into predicting what your thermal performance is, which as your geometry gets more and more complex is why you want to look at leading CFD softwares like an ANSYS IcePack or a FlowTherm to do the modeling for you so that you're not sitting down doing all these calculations to try and figure this out.
All right, this one's a little bit easier, Mark, from Bert Pinpin. Would you recommend using quick disconnect fittings?
Depending on the application, yes. A lot of customers are putting these cold plates into applications where, for reliability reasons, if their device fails, they want to be able to quickly and easily swap it out, in which case what they don't want to do is have to shut off the system, drain it of all the fluid, cut the pipe, take out the cold plate, put a new cold plate in place, and then have an extra joint in the piping assembly. Quick disconnects can be either connected directly to the cold plates or connected to the tubing that's coming out of them. Some of them are designed for what they call a blind mate, which means they can actually sit in the back of the cold plate. You just slide it into a rack and they'll automatically engage, and you just pull it forward to disconnect them. Others have a little push button on it that you'll actually push the button, and that allows your two halves of your quick disconnect to separate. Either of those are good methods for being able to swap a cold plate out of the system, either, again, for a repair or even just for a testing operation.
Okay. Next question comes from John Flavin. Is there use of tubing with internal insulation to electrically isolate the fluid from the base plate?
You might be able to use like I'm thinking of like a PEX tubing, something traditionally used in household commercial industry. The downside, so PEX tubing is a layer of plastic, a thin layer of aluminum, and then an outside shell of aluminum. The problem is any insulative layer that's there, like this plastic, is going to impede your thermal performance. It will give you your electrical isolation, but it's going to cost you in terms of thermal performance.
Okay, let's try this one from Randy Pone. Have you ever looked at tubing that has more internal area than a simple circular cross section, and what was the benefit?
I've looked at several different types of these. There are some commercially available tubings that are generally used in the large air conditioning industry that have either an internal fin inside the tube itself, or they have small grooves, or again, a different geometry inside the tube. In the cold plates that we've looked at and the experimentation that we've done, you get a little bit of a performance gain. A lot of it depends on what your fluid is, how fast is your fluid moving. Once the boundary layer in the tube gets built up, if you have very small grooves and your boundary layer is now thicker or is bigger than your grooves, you lose the benefit of the grooves themselves. So if you have fins, that's actually a better option. But that increased surface area also adds to the pressure drop associated with the cold plate. So it becomes a balancing act of how am I going to add this extra area and not go over the pressure drop that I can live with.
Okay, this question mark comes from M. Mursadeghi, who's asking, from a reliability and performance point of view, when do you prefer oil to water as the working fluid of your system?
I don't necessarily have a preference between the oil versus the water. It's usually dictated by what the customer's requirements are. If I had to choose, I would prefer water because it's going to give me the best performance. It's easier to achieve turbulent flow, which is going to give me my best heat transfer coefficient. Oils tend to be very viscous and into the laminar region, which is going to give you a lower heat transfer coefficient. So given a choice, I would prefer to stay with water as opposed to any of the oils.
All right, this question comes from John Carpenter. How realistic is it to buy a standard liquid cold plate to prove your application? To prove your application's need, rather.
So we have a lot of customers that will purchase these standards, whether it be the 180 or the full buried or the exposed tube, and do a basic mock-up. Prove out the technology, prove to themselves and their colleagues that this is the right way to go, that they can achieve their thermal performance, they can reduce their size, whatever the requirements are, and then come in and look at doing a custom solution where we physically lay the tube out specifically where their hotspots are. But a lot of customers do it, and they have great success with it.
Okay, couple questions left. We have about 90 seconds left in today's session. This question from Farhad Mohammadi again. What's the best manufacturing process, Mark, to have the best interface performance for copper and aluminum heat sinks?
If you have a copper tube and aluminum base plate, your exposed tube is going to give you your best thermal performance. You can set your device directly over the copper tube itself, thereby eliminating the conduction path into the physical copper. So you come out of your device through your interface material right to the copper and then into the water itself. If you do a full buried, you have to conduct either through a thickness of epoxy or through a thickness of aluminum before you get into your water stream. And all those resistances add up, and decrease your overall performance and efficiencies.
Okay, we are going to have to draw it to a close there. Mark, I think you get the prize for answering the most questions of any presentation so far at Thermal Live. We're counting 22 questions so far, and there were a few that we didn't get to. So if we didn't get to your question, don't worry, we'll be sending all of your questions over to Mark and his team at Wakefield-Vette. We'll get all the answers back for you. We'll post them on the Thermal Live site next week, so check back in a few days' time. And attendees, if you think of a question after the presentation, please just send us an email at info@electronicscooling.com. Don't forget to sign up for more presentations later today and tomorrow as well. We hope you enjoyed this presentation.